Okay, so let's go ahead and go over this one, and then we'll move on to the next one. So the first thing that we want to do is we want to draw this situation here, and what we can do is we can draw it in an initial state and a final state, so we kind of have a sense of what's going to happen here. So in the initial state, we have the block, and it's going to be moving with this velocity. For now, I'll just call it v0, but it's given a value of 5 meters per second. And then when it gets to the top, it has 0 velocity, but it's gone some distance we can call d. Okay. So now that we have our pictures here, what we can do is we can draw our free body diagram. So when we draw our free body diagram, we actually only have 2 forces acting on this. We have the force of gravity, which points directly down, so this is going to be mg, and we have the normal force. So the normal force always points perpendicular to the plane. That's what's meant by normal. And so now that we have our free body diagram in our picture, we can draw a coordinate system. A convenient coordinate system is going to look like this. So this is going to be the x direction, and this is going to be the y direction. The reason why I choose this coordinate system is the direction of motion is only along one of these axes. So it's, in this case, only along the x-axis. And the y-axis doesn't have any motion in that direction. So what that means, ultimately, when I sum my forces in general, the sum of the forces is equal to the mass times acceleration. Sum of forces in x is going to be equal to something. Sum of forces in y is going to be equal to something. Now, for completeness, I'll do the sum of forces in y, but we actually don't really care about that in this instance. So in order to resolve this, what we need to do is we need to look at this and say, okay, well, this normal force is completely in the y direction, but this force of gravity is kind of partly in the x direction and partly in the y direction. So what we need to do is we need to break it into components that are along this direction and along this direction. And the way that we can do that is we can complete some triangle here where one side of the triangle is in the same direction as the y direction. The other side of the triangle is along the x direction. And so we have this triangle that looks like this. Now, if I want to find the sum of forces in the x direction, then I just have to ask myself, for all of the forces acting on this block here, which ones are in the x direction? And it turns out that just this component of gravity is going to be in the x direction. This is going to be mg sine of theta, which is going to be equal to max. Now, this also has a negative sign because our positive x direction is going to be going up the plane, and this force is going to be going like this. Okay? Now, if we want to find what our sum of forces in y are going to be, we can do exactly the same thing. So we look and we see, okay, we have the normal force here, so we have n, and then we have a component of gravity along the y direction. This is going to be minus mg cosine of theta. And now, because this block is constrained to move only in the plane here, this is going to have an acceleration of 0. So this would let us solve for the normal force, but like I said, in this particular problem, we don't need it because there's no friction. Okay, so let's go back to looking at our sum of forces in x equation. We can actually reduce this a little bit by dividing both sides by the mass. And so when we do that, we end up seeing that the acceleration in the x direction is just going to be equal to minus g sine of theta. Okay. Now, what we're interested in is finding the distance that this block is going to go before it stops, and there's kind of 2 ways that we can go about this. One way is to use 2 equations. The other way is to use one equation that comes from the 2 equations. And so the 2 equation approach says x of t is going to be equal to x0 plus v0t plus 1/2 axt squared, and v of t is going to be equal equal to, this is going to be V0 plus AT, okay? Now, in this case, what we could do is we could use the second equation to solve for what the time is for it to go up the plane, because we know what the initial velocity is, we know the final velocity is 0, so that says 0 is equal to V0 plus AT, which in this case, A is minus G sine of theta, and so this tells us that we can move this around, or let me substitute this in first. So this is going to be V0 minus G sine of theta times T. Let's move this to the other side. So we have G sine theta T is going to be equal to V0, or T is equal to V0 divided by G sine of theta, okay? Is everybody with me still? I know I did this a little bit fast, but yeah.
So I did it without using time?
I'll show you how you can do that too.
Okay.
Yeah, they're equivalent ways to do this, but I kind of want to show both ways because people approach it different ways. Okay. So now that I have this time, what I can do is I can take that and plug it back into this equation, and then that's going to say that this distance d is going to be equal to V0 times this time, which is V0 divided by G sine of theta, plus, or in this case actually minus, because our acceleration is negative, this is going to be minus 1/2 times G sine of theta times this same time squared V0 divided by G sine of theta quantity squared. And when we do that, we end up finding a distance of 3.7 meters. Okay? It's funny, I know, right? So this was one way to do this, but you could have done this another way, and that's to use the VO-VF equation with the squares, right? So this one says that VF squared is going to be equal to V0 squared plus 2a delta x, okay? Now this equation, and we showed this one of the first classes when we were doing kinematics. This equation actually comes from these other two equations when the acceleration is constant. And actually these two equations are only are true if the acceleration is constant as well. So you could have also done this, okay? Any questions about this one? And feel free to stop me because I know I went through this a little quickly. Yeah?
What's under the VO squared that's at the far right?
Here? This is V's, really what it is it's this squared, because it's time squared, so it's V's, I don't know what's with the chalk today. V0 divided by G sine of theta quantity squared. Yeah, okay? Other questions? Okay, so I think the algebra here, while it's important, really isn't the most important part to us, because this is a physics class, it's not an algebra class. The thing that we really want you guys to be able to take away from this is really what I have written on the top board here. Being able to diagram what's happening with the situation, being able to say that this is the initial state, and this is the final state. And to be able to use those two things to write a Freebody diagram, being able to define a coordinate system, being able to obtain a system of equations to solve. So if this was a question on an exam, more than half of the credit would be on this. The rest of it would be on this. So this is the really important emphasis here, even though it's in terms of the work, not as much of the work. Okay? All right. All right, so we have another one here. So this one says, in a physics lab when studying concepts of Newton's laws, a mass M1, which has a mass of 3.5 kilograms, rests on a table with a slight roughness, where the coefficient of kinetic friction is 0.1, coefficient of static friction is 0.15. M1 is attached to mass M2, and that mass M2 has a mass of 2.8 kilograms with a light string over a massless frictionless pulley. Solve for the acceleration of the system when the system is released from rest. Okay? Let's go ahead and spend some time working on this one. Still going here? Yeah, it's 49 minutes. Nah, that'll work. Okay, so let's go ahead and talk about this one. So I already drew the situation that we have here. So we know that we have this block with some mass, I'm calling M1, that's on the table, and some block with mass M2 that's hanging off the side. And what we want to do is we want to find what the acceleration of the system is. So I drew the picture already here, so the next thing that we can do is draw a free body diagram for each one of these objects. So for the mass M1, we're going to have 4 forces acting on this. The first one is the tension force. So this is the force that the string is exerting on this, that's going to be pulling it off the table. Then we have the force of gravity. So this is going to be M1G. And we have the force of friction. So this is the force of kinetic friction because it's in motion. Finally, we have the normal force. So now that we have all our forces labeled for this one, what we can do is we can write down or we can draw a coordinate system so that we can determine which directions are going to be positive and which directions are going to be negative. Now, it's advantageous to draw this in such a way that either the plus x direction or the plus y direction is the direction that's going to move. In this case, the plus x direction is direction of motion. It's going to be pulled off the table. Okay, so that's the first one. We can do the second one now. So the second one is going to have tension acting up. Again, this is the force the string is acting on this. This is going to be pulling up. We have some gravitational force, M2G. Okay, and that's actually it for this one. So this is our mass M2. Again, what we'd like to do is we'd like to draw a coordinate system for this. So I'm going to draw this coordinate system pointing down because the direction that this mass M2 is going to be going down. Okay, so now that we have all this, we can write our sum of forces for each one. I'm going to start with block M1. So this one says that the sum of the forces, sum of vector forces is equal to mass times vector acceleration. Sum of the forces in the x direction is going to be equal to what? What are some forces that act in the x direction here? Tension, so positive or negative? Positive. Friction is there too. Is that one going to be positive or negative? Negative. Minus Fk. Is that it? Yep, that's it. So this is going to be equal to the mass M1 times the acceleration. Okay. Now let's sum our forces in the y direction. Sum of forces in the y direction. What do we have? Normal force. Somebody from back here. What do we got? What else do we have? We have gravity, right? So this is going to be minus M1G, and this is going to be equal to the mass times the acceleration in the y direction. But because this is constrained to stay on the surface here, this is going to be equal to 0. Okay? So that actually allows us to solve for the normal force, and so the normal force is just going to be M1G. All right. Now we can do the same thing with our second block. And so for our second block, what we have is the sum of the forces in the y direction is going to be equal to what? Now be careful here with the signs because of the direction that I chose to define to be the direction it's going to move. So what do you guys think? What are the forces that I have on this one? So tension, is tension going to be positive or negative? Negative. So it's going to be minus T. What else? Weight, or the gravitational force, right? So I thought you were telling me to wait. Okay, and this is going to be equal to M2 times A. Why is gravity positive? Why is gravity positive? It's because I chose to define my coordinate system so that down's positive. I'm choosing the direction it's going to move to be positive, and so the force of gravity is the same direction as the way that it's going to move. The tension's the opposite direction. And so you see when I wrote this equation here, tension's negative, gravity's positive. Okay? Yes, exactly. So the next thing that we see, and I'm going to write this right here, there's a nice little trick that we can apply to solve this fairly easily. And that's to say, okay, well, if I look at these equations, this one has a minus t, this one has a plus t. In order to eliminate the tension, I can take these and I can add them together. And so when I do that, I end up canceling my tensions. This is going to be m2g minus fk is going to be equal to m1 plus m2, parentheses, times a. Okay? Solve for a. A is going to be equal to m2g minus fk divided by m1 plus m2. And now the last thing I can do is I can define what fk is. Fk is going to be equal to the coefficient of static friction times the normal force that I solved for here, or sorry, this is kinetic friction, times the normal force that I found here, which is going to be m1 times g. Okay? And so between these two equations, I have the solution fully parameterized. And when I come over and I look at what the answer is here, we should find that this acceleration A is going to be equal to 3.8 meters per second squared. Okay? Any questions about this? Okay, so let's move on to another one. All right, now this is an interesting one. This is an interesting one. Still follows the same spirit as the last ones we've done. Process to start is exactly the same. The way that the forces are going to manifest themselves in our sum of forces is going to be a little bit different. But the process is, as I say, almost exactly the same. So go ahead and talk about this one. Okay, so let's go ahead and talk about this one. So here's the setup that we have here, where we have this mass M1 and this mass M2. And so the first thing that we'd like to do here is to draw a free body diagram. So we have, surprisingly, I know, right? So we have our mass M1. So when we draw the forces acting on this, we're going to say that this is going to be a normal force. This is going to be a force of gravity, m1g. We have tension, and then we have a force of friction. Now, you can make the assumption either that it's going to move or it's not going to move. When I did this, I assumed that it wasn't going to move, so what I said was this was some static force of friction. You can make the assumption that it's a kinetic force of friction, and we'll talk about what the consequence of that is going to be afterwards. So this is what I ended up having, and then you have your coordinate system here. This is going to be your x, this is your y. So then we want to do a free body diagram for the second one. For the second one, we had some normal force, we had some gravitational force, m2g, we had some same tension, and we had some force of friction, F sub s. And just to denote these a little bit differently, I'm going to call this F sub s1 and F sub s2, is mass m2. Okay. For this one, we're going to draw our coordinate system to look like this. So this is the plus x direction, this is plus y direction. Okay. So now, what we can do is erase the board and write our sum of force equations for each one of these masses. Okay? So when we do that, for the first one, we're going to see that the sum of forces in the x direction is going to be equal to t minus fs1, which is going to be equal to the mass 1 times the acceleration. Sum of forces in the y direction is going to be equal to n minus mg, m1g, which is equal to 0, which says that n is going, and let's call this n1. n1 is going to be equal to m1g. Okay. Now let's look at the second one. So the second one says that the sum of forces in the x direction. Now we have to break this gravitational force into components. So this is going to be the angle theta. And when we break that into components, we see that the portion that I'm interested in the x direction is going to be this m2g sine of theta. I'll just write our m2g cosine of theta here as well, because we're going to use that in a second. So this m2g times sine of theta is going to be in the positive direction here. So this is going to be m2g sine of theta. We also have a minus t. We have a minus fs2. And then this is going to be equal to m2 times the acceleration a. Okay. Now when we sum our forces in the y direction, we see the sum of forces in y is going to be equal to n2 minus m2g times cosine of theta, which is equal to 0. And so we see that n2 is going to be equal to m2g cosine of theta. Okay. Now, let's look at our equations in the x direction. So if I look at this equation and I look at this equation, we can apply the same trick that we did in the last problem, and that's to add one equation to the other in order to cancel what the tension is. So when I do that, what I end up seeing is I find that m2g sine of theta minus fs1 minus fs2 is going to be equal to m1 plus m2 times a. Now that we're here, we want to pause and ask ourselves something. Is this value that I get when I take the difference between this and this going to be positive or negative? So if it's positive, that means that this can accelerate. If it's negative, it means that it's going to stay at rest. And so what does it mean if this is negative? It means that the largest value of the force of static friction is going to be larger than the component of gravity that would cause us to move in the first place. And if that's true, then this force of gravity can't overcome the force of static friction. And that ends up meaning then that it can't accelerate. And so when you calculate these values here, you end up finding that the force m2g sine theta is about 29, and then this one is about 38. And so this ends up giving you some negative value. These are in newtons, which tells you then that this actually can't accelerate. Now, you could have done this the other way, and you could have said, okay, well, what happens if I plug in the force of kinetic friction instead? You'd find the same thing, that it's not going to accelerate. But there's kind of, I mean, if the force of, if the net force of kinetic friction, when you plug it into the equation, gives you a negative sign, you're still in good shape. But there's this funny spot in the middle where you could find that this force can't overcome the force of static friction, but it can overcome the force of kinetic friction. And you have to be careful if you use the force of kinetic friction in that case, because it wouldn't actually move, and your answer would say that it would. So here, if you're trying to determine if something's going to move or not, it's always better to do it in terms of the force of static friction. Okay. Any questions about this one? Yes.
So since the force of static friction equation is the less than or equal to.
Right.
What do we do?
Right. So really, and this is the really important part to this. Force of static friction, I didn't write this. This is less than or equal to mu s times n. So what's really going to happen here? The force of friction is never actually going to cause this to move like this, right? That would, I mean, Elon Musk would be pretty happy with drilling his tunnels and sending things to space if friction could make things go. So clearly that's not the case, but it's because of the inequality, and it's the less than. If this doesn't move, then the sum of these two forces of static friction are going to be equal to the force that's exerted here, not equal to the coefficient of friction times the normal force. Coefficient of friction times the normal force would be larger than this. So that's why you have to consider the inequality and the fact that these can come up to a maximum value, and if I assume that maximum value, what that tells me is this is going to move backwards, right? Which is actually what you don't want. This is kind of an exercise in showing why it's important to consider the inequality and not the equality, because you get a negative acceleration that doesn't make sense.
So when you solve for u sub s times like the normal force, can you just solve for it?
You could, yeah, and that's actually how I came up with this 38.
38.
I came up with that by taking my normal forces and then multiplying by their respective coefficients of static friction and then adding them together.
So that's very easy. So you would just assume the equal to?
Yeah, I assume the equal to, and then I said, if I assume they're equal to, does this give me something that's positive or negative? If it's negative, it's non-physical because it can never accelerate backwards.
So if it's negative, we can't do.
Right. Well, it's not that you can't do the problem, it's that it never would have started moving in the first place. That's what that's indicating. Okay? All right, so
Static friction indicates that it's not moving anyway.
right. So what I did was I assumed a value larger than the value of the force of static friction actually would, by assuming that it was the maximum value it could have.
So the maximum value it has is that 38.
Yes, the maximum value it can have is by saying that the force of static friction is equal to mu s times n. But it's less than or equal to, it's not always equal to. And if something's not moving, so say for instance, I have this eraser on the table, I'm applying a force to it, but it's not enough to make it move. The force of static friction is identically equal to the force that I'm applying. It's not equal to the coefficient of friction times the normal force, because if that was true, that would say that the eraser should move backwards on its own, and it doesn't. Okay.